So first of all, I want to say thanks for the invitation. It's a pleasure and a great privilege to be speaking this trimester. So I spent the weekend, it was a beautiful sunny weekend in Scotland. So I spent the weekend up in the mountains, which means two things. I've turned into a lobster, as you can see. And also I'm pretty exhausted. So I would very much welcome a lot of difficult questions to keep me on my toes. Okay. So I'm going to talk about the helical maximal function. So this is a project which is joint with a number of colleagues in University of Wisconsin-Madison, so David Beltran, Shaoming and Andreas Seeger, who I believe is in the Institute right now. So I'm going to kind of begin quite gently and talk about some very classical topics related to this helical maximal function. So in particular, I want to motivate this topic by discussing the weird and wonderful concept of a nicodem set. So so here we're going to let E be some subspace of the Euclidean plane and with positive measure. And the question is already interesting if we just take E to be this unit square. And what we're going to do is for each point X in E, we're going to ascribe to it some choice of line. So for every point, we have a one parameter family of lines to choose from. And these are all possible lines that pass, say, unit line segments with center through X, okay? So we have a one parameter family corresponding to all the possible directions. And as we move from point to point, we're allowed to independently choose one of these lines. And our problem is just to compare the size of this line set formed by the union of these lines and E itself. So maybe there's some issues with measurability. If you take out a measure or something, I think this is well defined. So that's the basic question. But of course, this doesn't really make much sense because we've trivially got this inclusion relationship. So we know that the union of the line segments contains the set of centers. So we can say that the union of line segments is bigger than the set of centers in any meaningful notion of size. So what I'm going to do is take a step back and make the minimal change possible to make this problem non-trivial. So what we can do is instead of taking these whole lines, we're going to take the punctured line segments. So we're going to remove the center that lies in the set E. And once we do this, of course, we don't have this inclusion relation. So the problem becomes a bit more trivial, a bit more non-trivial. And in fact, what's surprising is we no longer have this size relationship between the two sets. And in particular, there's a classical construction described to nicodem from the early 20th century. And it says that you can ascribe a line segment to each point in, say, the unit square, such that if we take the union of these punctured line segments, this has measure 0. So of course, this is a bit weird and unnerving because we've started off with this set of positive measure. We've replaced each point with a continuum of points, but we've ended up with something smaller, okay? And so this kind of construction, of course, now plays a very central role in modern harmonic analysis. It underpins a lot of behavior of operators related to the Fourier transform in higher dimensions, but maybe I'm not going to talk so much about that. So we're going to be interested in variants of this nicodem set construction, or the theory of these nicodem sets. And in particular, I'm going to be interested in taking these line segments and replacing them with families of curves. And the most prototypical example of this is to consider nicodem sets of circles. So here we have exactly the same situation. We're going to have a subset of the Euclidean plane with positive measure. And then for each point in this set, X, we're going to ascribe a choice of circle. And exactly as before, we have a one parameter family for each point, so that now it's parameterized by all the different radii, okay? And now, of course, we no longer have this trivial comparison that we did in the naive problem from the previous set. So it's already non-trivial to ask, well, can we compare the size of the circle set, the union of the circles, with the set of centers, okay? And it turns out in this case, things behave a bit more as you'd expect. And there's this celebrated theorem of Marstrand from the early 80s. And it says, well, if the set of centers has positive measure, then the union of all these circles has positive measure. Okay, so this nicodem phenomenon that we saw for lines does not hold for circles. So I guess on its own, this theorem doesn't look that surprising, but when you contextualize it by comparing it to the case of line segments, then it turns out to be a rather subtle result. And indeed, Marstrand's proof is rather beautiful and ingenious. Are there any questions about this before I move on? Okay, so in this talk, I'm going to be interested in kind of functional analogues of these kind of questions. And in particular, this I want to start by discussing a functional version of this Marstrand theorem. And here we're going to be interested in an operator, which is called the circular maximal function. So this is an object that, of course, many people will be familiar with here. So this circular maximal function takes as its input some function, say, in the continuous function on the Euclidean plane. And what it does is, well, we fix the center x, and then we take averages of this function over all concentric circles around x. So this is what this inner integral is doing. And so we're integrating the function over this circle with respect to a normalized arc length measure on that circle. So each of these, the measures all have mass 1. And then we take the supreme of the absolute values of these averages over all these radii, okay? So this gives us some variant of the Hardy Littlewood maximal function, but now instead of averaging over balls, we're averaging over these low dimensional sets, these circles. And the first question we'd like to answer here is, well, is there an analog of the Hardy Littlewood maximal theorem? Can we determine the range of LP for which this maximal function is bounded? And this question was answered by Bourgain in the 80s in another celebrated work. And well, this states that for all p bigger than 2, this circular maximal function is bounded on LP. And this turns out to be the sharp range for which this holds. So I want to make a few remarks about this circular maximal function theorem. It's kind of a prototype for what I'm going to be discussing later. So first of all, you can think of it in some sense as a quantitative version of Marstrand's theorem. And in particular, if you have any of these LP bounds for the circular maximal function for any finite value of P, okay, then you immediately get Marstrand's theorem. So Bourgain's result is like a super strengthened version of Marstrand's theorem. And okay, so the proof of this is pretty direct. I've written on the slide, but maybe I won't go through it. You basically just test the inequality against the characteristic function of, say, this union of the circle set, roughly speaking. And as I mentioned before, the range p bigger than 2 is sharp. And well, you can see that 2 satisfies this nice property that 2 is equal to 2 divided by 1, which is the dimension of the ambient space divided by the dimension of the circle over which we're averaging. So this doesn't really mean anything as written. It just looks like coincidence, I guess. But there's this general pattern with these kind of geometric maximal functions where you get this kind of numerology. And so one thing I'd like to highlight is this range of boundedness is open, of course, p strictly bigger than 2. And when we look at the what happens when p equals 2, where we have no kind of endpoint there, it's not even restricted weak type 2,2. So even the weakest Lorentz space bounds fail to hold. This was observed in a paper of Seeger, Tau, and Wright, and uses some kind of K-type construction. So I'd like to highlight this because the failure of this endpoint is kind of points to some subtlety in the analysis of this operator. You can't just shoot for an endpoint estimate and hope to interpolate it to prove this kind of estimate. Okie dokies. So this is a kind of very brief tour of some of the classical topics. So now I'm going to move on to our main result and the objects that we were interested in studying. So the basic question we wanted to tackle was to establish some kind of higher dimensional version of Bourgain's circular maximal function theorem. And here there are 2 directions in which one can travel. So we can go down the codimension 1 route, and that means we're going to take the circular maximal function in the plane and generalize this to spherical maximal functions in high dimensional Euclidean space. However, it turns out that these spherical maximal functions, when you're averaging over hypersurfaces, are actually significantly easier to study in higher dimensions than the circular maximal function. Indeed, this was already famously, the sharp range of boundedness for these operators was already famously established by Stein in the 70s. So this was some 10 years before Bourgain's circular maximal function theorem was proved. So that's not a very fruitful direction for us to go in now. So instead, we're going to go down the dimension 1 route. So we're going to generalize circles in the plane to curves in high dimension, so space curves in high dimension Euclidean spaces, okay? So it turns out that this operator is quite challenging to study, and it kind of, well, the analysis of these operators contains as a subset all the difficulties you have when studying the circular maximal function on the plane. Okay, so these become much more difficult to study in high dimensions. Prior to our work, as far as I'm aware, there was only really one paper that made any significant inroads on this problem, and that's due to Pramanik and Seeger, and it's from about 2007. And they were interested in the three-dimensional case. And I'll come back to this paper in a few minutes. Okay, so let's try to make this discussion a bit more precise. So here I'm going to be focusing on this helical maximal function. So we're going to really just focus on the three-dimensional case. And it's defined in an analogous manner to the circular maximal function. So here now we're going to take as our input some function, say a continuous function on R3 rather than the Euclidean plane. And we're going to take averages of this function over concentric helices. So we'll fix a center X, which is going to be the point our helix is centered around. And then we'll vary over different radii t, and we'll draw helices around that point X with which are going to wrap around, I don't know, wrap around the vertical axis around X in like a tighter or looser circles, depending on the value of t. So then we take the absolute value of these averages and we take the supremum over all these kind of the radial parameter. And so again, we're interested in trying to study the LP bounds for this operator. And our main result is that this operator is bounded for all p bigger than 3. Okay, so this is, as I said, joint with David Beltran, Shaoming and Andreas Seeger. And I should point out that, like in the same week, a group in Korea, Ko-Leo, proved the same result. So their methods are, there's definitely some similarities between what we do, but I think there are also some essential differences. So it's quite nice the two papers in some sense complement one another. Are there any questions about this definition or anything like that before we go on? Okie dokie. So I want to make some comments about our theorem. So I mentioned before there was an earlier work of Pramanik and Seeger. So they managed to establish this bound amongst other things for p bigger than 4. And so our contribution is to close this gap between 3 and 4. The theorem implies a Marstrand type theorem now for helices. So if you try to draw helices around centers of points and compare measures of sets and stuff, you get the same result as in the Marstrand theorem. And but this is already a consequence of the Pramanik and Seeger result, because you don't need any quantity. You just need a finite value of p for that to hold. So importantly, the range of p bigger than 3 is sharp here. And more generally, if you're trying to study the problem in Rn, if you've got a suitable class of curves that generalize a helix in R3, then you can expect this operator to be bounded for p bigger than n. And once again, we see this relationship that n is the dimension of the ambient space divided by the dimension of the curve. So it fits into this general numerological scheme. So I've picked the helix here just for simplicity. Our result holds for all curves in the Euclidean 3 space, which have non-vanishing curvature and torsion. And if you want to study this problem in high dimensions, then the right class of curves to consider are curves that have non-vanishing curvature functions. So you have the n-1 curvature functions coming from the Frenet frame, and they should all be non-zero. And that's kind of the model class of curves here. So I forgot to mention, actually, I might try to go back to the previous slide. So the group in Korea have also managed to prove results in high dimensions now, but they're not sharp, but I think they're quite impressive, because before, no finite value of p boundedness was known for these operators. So they have results for these classes of curves of non-vanishing curvature in high dimensions. Okay. So for the remainder of this talk, I want to kind of give some flavor of the ideas that go into our work. And basically our approach follows methods that were introduced in the early 90s to give alternative proofs of the circular maximal function theorem. However, in order to study this thing in high dimensions, we really have to make use of a lot of tools in Fourier analysis that have only recently become available, in particular kind of tools from multilinear restriction theory and things like that. So for the next section, I'm going to go back to this work from the early 90s and describe the main ideas that crop up there, and maybe in a somewhat loose fashion. I'm not going to dot all the I's and cross all the T's here. And then at the end, I will give some indication of the difficulties that arise when working with these operators in high dimensional space. Okay, so let's begin this discussion. So of these classical methods, which are based on Fourier analysis. So I want to try and give you an idea of how the Fourier transform comes into play here. So let's consider some maximal function associated to a family of curves. So this capital gamma here, it could be either these circles or these helices, either one will work here. And I'm going to make a slight modification to our definition. So now I'm just going to take a supremum over this compact range of radii between 1 and 2. And it turns out you can do a simple reduction using kind of Littlewood Paley theory. It's well known to reduce the problem to studying this localized operator. So this family gamma of curves is given by translating and dilating some fixed seed curve, so either a circle, unit circle, or a helix centered at the origin. And consequently, we can write these averages in terms of convolution. So here we have a convolution of f with some dilated surface measure, where this surface measure is ascribed to the seed curve. And I'm going to write this convolution as, I'm just going to introduce some notation as this operator A, but in the A, I'm going to build in this localization, the t variable, into our operator A, okay? So A is a product of this convolution with also this, this cutoff function rho. So at the moment, all we need rho to satisfy is that it's bounded below when t lies in our compact range of radii. And we can choose a function rho, which also has Fourier support in this interval between -1 and 1. We don't need that now, but this will be useful later on, okay? So this is just our localized averaging operators. Okay, so we have these averages, which are written in terms of a convolution operator. So of course, now this is Fourier analysis's chance to shine, because Fourier analysis loves convolutions. We can write this, this convolution as a Fourier multiplier. So that's what we're going to do. We're going to take this expression and we'll write it on the Fourier side. So what happens on the Fourier side? Well, we're just multiplying by the Fourier transform of the dilate of this measure, okay? Which turns out to be this expression here. So it's, I'm drawing in white, which is just rubbing things out, this expression here. Okay, so so now the question really is to understand the behavior of this Fourier multiplier on the Fourier transform side, okay? And temporarily, I'm going to focus on the case of the classical case where we're dealing with circles. And one nice thing when we do for the circular measure is that we have this formula, which is very classical, and it comes from the stationary phase method. And this Fourier transform can be written as, well, there's a sum of two terms, but the two terms are very similar to one another. So I'm going to kind of brush this under the carpet a little bit. They only really change by this sign here. So let's just focus on one of these terms. So each term is made up of two factors. We have a decay term, which is given by some symbol of order 0. So that's not going to play much role in the analysis, so we can kind of ignore that. But importantly, we have this decay factor, which is decaying like xe to the -1/2 as we go off to infinity away from the origin. Okay, so we have some decay. And also we have this highly oscillatory factor. So we have this e to the I norm of xe. And so these two features of this multiplier are going to play a role in our analysis. We'll have to make use of the decay and the oscillation, and I will be referring back to them frequently. Okay. So we can take this formula and we can plug it into our Fourier transform expression. Let's do that. And we get something like this. So these averages are roughly speaking equal to this is an example of a Fourier integral operator. So we have this Fourier integral, and again, we see we have this decay term, which appears here, and then we have the oscillatory term, which is now coming into this phase here, okay? And if you've got a sharp eye, you can see that this, this can be written in terms of some well-known, well-studied operators. So in particular, this oscillatory term corresponds to the multiplier of the Euclidean wave or half-wave propagator. And then we have the decay term, which is just some inhomogeneous pseudo-differential operator. Okay, so this formula relates the study of these circular averages to solutions of the Euclidean wave equation. And this connection was kind of well fleshed out and exploited in works of Sog and Mockenhop, Seeger, Sog from the early 90s. And in particular, they showed that certain estimates for solutions to the wave equation, space-time estimates called local smoothing inequalities, imply the circular maximal theorem. Okay, so I'm not, although we do take this approach in our work, I'm not really going to go into the details of what this local smoothing involves, but basically this encapsulates this relationship between the wave equation and the circular maximal function theorem. Okie dokie. So, I did the wrong thing. So, to analyze this operator, we're going to have to take into account the two distinct features of the multiplier, which have, as I mentioned before, is the decay and the oscillation. So I'm going to focus first on the decay. So in order to exploit the decay, we're going to use a Littlewood Paley decomposition. It's kind of the obvious thing to do here. So we're going to introduce this family of Littlewood Paley projections. So I'm denoting these by beta d over lambda. So what these do is, well, on the Fourier side, they just cut off the frequencies to some annulus lambda away from the origin of width lambda. Okay, so the support of this function beta xe over lambda is in this green annulus, and these operators are the Fourier multipliers associated to these functions. Okay, so once we do that, well, if we've localized this decay factor to this annulus, then it has size lambda to the minus 1/2 everywhere. So basically, we can take this this multiplier and replace it with a lambda to the minus 1/2, just some constant. And what I'm going to do is just factor out these lambda to the minus 1/2 and just consider the operator now just with the frequency localization. So of course, we can't really forget about these lambda to minus 1/2. These are important because when we want to sum together all these frequency localized pieces, they're going to help us to sum together the pieces. They're going to give us some geometric decay. But we can deal with that later. And now we're just going to focus on the operators with these terms factored out. Does this make sense? Okay. So that's us taking into account the decay. And now we want to understand how the oscillation plays a role in our analysis. So we're going to look at the oscillatory term. And the key observation here is that these operators have have the special spatio-temporal frequency support. So what do I mean by this? Well, let's write out the operator. And what I'm going to do now is take a Fourier transform in the t variable. Okay, so this is the variable corresponding to the radius of the circle. Okay, and what happens when we do that? Well, I'm just going to apply the formula for the Fourier transform. So we're going to integrate over the real line. We're going to have an e to the minus I t tau. And then, okay, I'm going to use Fubini, pull this integral into the R2 integration. We're going to have this other e to the it xe. So I can couple that and we get a minus norm of xe here. We've got the rho t function, and then I close the t integration. And then we've got all the other terms that are independent of t. Okay. So something like that. So this is the expression we get when we take the Fourier transform in t, just by using the formula for the Fourier transform. And tau here is, of course, the dual variable. And what we notice is that this inner integral is simply the Fourier transform of our rho cutoff, evaluated at tau minus norm of xc. Okay, and remember this rho was chosen to have Fourier support in a compact region. So this is that we have the special support properties for the tau xc variables coming from this. Okay, so I'm just going to rewrite this. So if we think of if we now take the x Fourier transform, so now we're taking the whole xt Fourier transform and all the spatio-temporal variables, then what we get is, well, it's kind of like a multiplier. We've got the this rho hat of tau minus xe, then we've got our dyadic frequency localization, and we've got the Fourier transform of input function. Okay. So I want to understand the support of this this function appearing in the spatiotemporal Fourier transform. That's pretty easy to do. So first of all, we have this tau minus xe is going to be localized at unit scale. And this means if we think of this in the three-dimensional xe tau space, we're localized to a one neighborhood of the light cone. Okay. Well, I've just written the top side, but it's a doubly infinite light cone. And we've also got this beta function, and this is going to localize xe to be about size lambda. So we're going to truncate this light cone to a piece that's about height lambda away from the origin. So it has radius lambda, and then it has height lambda. Okay. So this picture shows us this xe tau support of these localized averaging operators. So we now have a function with frequency support around this cone, and the cone is of course quite a curved object, and this makes it slightly difficult to analyze this operator. So the typical approach one takes in such situations is to break up our curved surface into a union of convex flat boxes. Okay, and this is what we're going to do. So we perform what's known as a plate or a Planck decomposition of this cone. So we take the cone, we divide it up into these pieces. These are chosen to be boxes, just rectangles, with dimensions that are kind of adapted to the geometry of the cone. So they have width 1 in the normal direction to the cone, corresponding to the fact that we're on a one neighborhood of the cone. They go all the way down the flat length of the cone, so they have length lambda in the flat direction. And then importantly, they have width lambda to the 1/2. Okay, and this lambda to the 1/2 is chosen in light of the curvature of the cone. So if you choose this length lambda to the 1/2, these pieces just fit nicely around the cone. Okay, so these are kind of convex approximations to these pieces of the cone. So these plates I'm denoting by theta here, and we're going to take our operator and we're going to write it as a sum of operators a lambda theta. So each of these a lambda theta is just localized to have support on one of these theta Plancks. So this is just performing a partition of unity in this frequency space. Are there any questions about this? Okay. Okay, so the main difficulty now is to take into account the oscillations between these different pieces in this sum. So we've got this sum of different terms. We should think of each of the individual terms as being relatively simple because of the convex nature of this shape. So I'll come back to this a bit later. But we need to understand how they interact with one another in this sum. So each term oscillates with a certain frequency. All these frequencies are disjoint by definition because they correspond to disjoint pieces on the cone. And so we need to understand their constructive, destructive interference patterns. And the key tool, there's a number of different ways to do this, but probably arguably the most effective is to use a square function estimate. Okay, so what we have here is we can say that on average, in the sense of the L4 norm, that if we can compare the sum of these pieces in the decomposition with this square sum. Okay, so of course, if we just trivially bounded this thing by applying Cauchy-Schwarz, then we get some similar looking inequality, but we're going to lose in the number of pieces in the sum. Okay, so we get this pointwise inequality, but we're going to lose by a factor of, I guess, lambda to 1/4, which is the number of Plancks to the power of 1/2. So this is just by Cauchy-Schwarz. However, this Cauchy-Schwarz inequality is not taking into account the fact that these there's going to be interferences between the terms of this sum. Okay, so so this square function takes into account this interference and shows that it gives you a gain of lambda to 1/4 over this trivial inequality. So of course, if these were just all non-negative functions, then we couldn't say anything better than this Cauchy-Schwarz bound, but we get this improvement. So the square function estimate I've written here is kind of the best possible, and it was proved pretty recently in a really remarkable paper of Guofwang and Zhang. But for the purposes of proving this circular maximal function theorem, we actually, it suffices to consider much weaker estimates. So there's a version of this square function inequality due to Mockenhop, Seeger, and Sorg, which has some power of lambda that beats lambda to 1/4, but it's not just 0. And that's already enough for proving the circular maximal function theorem. Okay, any questions about this? Okay, so this square function inequality takes into account the interference patterns between the different terms of this sum, and then we're left with what are essentially kind of positive operators to analyze. So let's look at these individual terms of the sum. So if we now in absolute value. So to understand these individual pieces, we can just apply the uncertainty principle. So you'll remember each of these individual pieces on the Fourier side is localized to one of these planks, which have these particular dimensions. So it's a lambda to 1/2 times 1 times lambda plank. And by the uncertainty principle, we expect this on the spatial side, this function to be localized on translates the dual plank. So the dual plank is the plank with the same orientation, but we take the reciprocals of all the side lengths. So now this is a 1 by lambda to the -1/2 times lambda to the -1 plank, okay? So by the uncertainty principle, if we look at this function on the spatial side, it's just going to look like a tiling of the Euclidean space by all these planks. And on each plank, the function is essentially constant. So we can think of this as just being a weighted sum of characteristic functions of these planks in this tiling. Because this is a relatively simple object. However, we have to take into account that there are many different pieces with so that we have all the different planks coming from this decomposition, and they have all different orientations. So really what we have here is a kind of superposition of functions that look like this, but they're all orientated in different directions. So this is corresponding to plank θ1 orientated this way, θ2 is orientated this way, and so on. So what we can do is we can take this, we can essentially replace these a lambda thetas with these weighted sums of characteristic functions, and then we have to understand the resulting expression here. And to do that, we have to understand how these planks which point in different directions can overlap and intersect with one another. And the key tool here is to use some kind of Kicker or nicodem maximal estimate. So I don't really want to go into details of this part of the argument, but that's like the final stage in the argument, and it just relies on well, I mean, these bounds are kind of actually relatively simple now. Okay, it just relies on this geometry of these directions separated planks rather than any kind of Fourier analytic input. Okay, so that's a kind of vague overview of the ideas that go into the Fourier analytic approach to the circular maximal function theorem. And now I want to talk about how one can adapt these ideas, or what new difficulties arise when we try to implement this program in the case of the helical maximal function in R3. So before I move on, are there any questions about this? Okie dokie. So let's start to look at the new features in the helical case. So let's go back to the start and recall the initial steps of our analysis. So you remember way back at the start, we took at these averaging operators and we wrote them as Fourier multipliers. And the multiplier is just the Fourier transform of the dilated measure on our curve. So in the case of the circle, we had this very simple formula coming from stationary phase. And in the helix, we can also analyze this multiplier using stationary phase techniques. So here I've written the multiplier in the case of the circle. So this is just what we had before. And you remember that there's this xc to the -1/2 decay. Okay. And an important feature of this multiplier for the circle is that it doesn't matter which direction you go in the Euclidean 2 space, you always have the same rate of decay. Now this property does not hold at all when you're dealing with the helical maximal function. So there are certain directions in R3 in which you can travel where the multiplier is decaying at one rate, and then other directions where it's decaying at a different rate, and you have to kind of take it into account of this. This is an essential difference between the two problems. So I want to try and make this a bit more, well, explain why that's the case. So we're going to let gamma denote, say, an arc length parameterization of the curve we're working with, say our helix. And we take our measure d sigma to be defined through this, this formula. So if we're testing the measure against a function f, all we're doing is precomposing f with this parameterization and then integrating that against some cutoff function chi. So chi here is just some smooth cutoff function. So when we take the Fourier transform of the measure, when it's written in this form, we get a simple oscillatory integral expression. So we have an oscillatory integral with some amplitude, which is our smooth cutoff, and then we have a phase, which is the inner product of our parameterization with the frequency vector xe. Okay. And we want to understand the size of this, this oscillatory integral, so we're going to apply stationary phase method. So the stationary phase method immediately points us in the direction of what I'll call these critical cones. So we know that if this phase function does not admit any critical points, the derivative does not vanish, then we're going to have rapid decay of this oscillatory integral. So we have to home in on the values of xc in R3 for which the phase admits a critical point. And that I've denoted by sigma 1, okay? So sigma 1 is just all the points where there exists some point s in the support of the amplitude function for which the derivative of the phase is 0. And this is I guess it's a codimension 0 cone in R3. So this fills out a positive proportion of the R3 space. So localizing to this isn't a big deal. However, we also have to distinguish between the nature of the critical points. So here we can have a situation where the critical point is either non-degenerate, meaning the first order derivative vanishes, but the second order derivative is non-zero, or there can also be degenerate critical points, and that's the kind of really bad situation. So this leads us to consider another cone, which I'm calling sigma 2, and sigma 2 is the points in R3 where the phase admits a degenerate critical point, okay? So there's a point where not only does the derivative of the phase vanish, but the second order derivative of the phase vanishes, okay? And you can see that this is going to be basically codimension 1 cone in R3, okay? So this is a lower dimensional subset of R3. So these two cones are going to be fundamental to understanding our Fourier multiplier. So in particular, we can apply van der Corput, and what van der Corput tells us, oh, I've kind of written over my own, oh, no, maybe, can I get rid of all this? Yes. Right. So what does van der Corput tell us? So if we're really far away from the first critical cone, like I said before, then we have no critical points, and so the Fourier transform is rapidly decaying. So that's an easy portion of the operator to deal with. Now let's suppose, well, we can be close to sigma 1, but we're far away from sigma 2 where the critical points are degenerate. Well, then we only have non-degenerate critical points. And this situation is similar to that of the circular maximal function, where we get a decay rate of xe to the -1/2. Okay. And then there's the third situation. And the third situation, we're right on top of this sigma 2. We're really close to sigma 2. And that's a really bad case where we can have critical points and they're degenerate. And in that case, well, we can still ensure we have a decay of xe to the -1/3. So why is that? Well, if the first two derivatives vanish, then we can guarantee that the third order derivative does not vanish. And the fact that the third order derivative does not vanish is basically equivalent to the fact that we're working with curves with non-vanishing curvature and torsion. So this is to do with the geometry of the curve. So if we're working with the helix, you can see at any point where the first two derivatives vanish, the third derivative is necessarily non-zero. Okay. So the worst case is we get an xe to the -1/3 decay rate. So this situation at the top here is pretty trivial, doesn't really play any significant role in the analysis, but the fact that we have these two different decay rates of xc to the minus 1/2 and xc to the minus 1/3 does play a significant role in what's to follow. Are there any questions about this? Okay. So let's try to understand the geometry of these cones sigma 1 and sigma 2 that I introduced in the previous slide. So in particular, let's look at sigma 2. So we can see, right. I don't know what I'm doing here. Right, okay. Oh, there we go. So this is just recalling the definition of sigma 2. It's the points in xc and R3 that admit a degenerate critical point. So if we're working with an arc length parameterization of our curve, then we can understand these conditions in terms of the Frenet-Serre frame on the curve. So in particular, this first order derivative of gamma is just the tangent vector field to the curve. And this second order derivative is going to be the normal vector field to the curve. So these conditions mean that xc is simultaneously normal to both the tangent direction and the normal direction to the curve. So that means that xc must be parallel to the binormal direction to the curve. Okay, so I've drawn this here. So xc is some point which lies in the orthogonal space to this the span of n, s, and ts. So it's lying in the span of bs. And that means that we can, I've done the same thing again. That means we can characterize this sigma 2 cone as the cone generated by this binormal vector field. Okay, so in particular, if we think of this binormal vector field as being some curve in the two-dimensional sphere in R3, then sigma 2 is the cone generated by that curve just by multiplying it by some scalar lambda at every point. Okay. So there's a simple kind of geometric characterization of this sigma 2 cone. So the relevance of this binormal cone to the analysis was already realized in the work of Pramanik and Seeger, mentioned before. So I'm going to split the discussion up into three cases. So first of all, I'm going to consider the case where we're really far away from this cone sigma 2. And this is the kind of non-degenerate situation. So in particular, I want you to imagine localizing our operator. So here this is the frequency localized operator A lambda f to points xc, which are in this cone sigma 1. So that means we're in the situation where the multiplier is not rapidly decaying, but they're far away from sigma 2. So we're far away from the degenerate critical points, okay? So the picture is something like this, okay? So say this is our sigma 2 cone, and we're distance, say, lambda away from it, that we're supported in this green region when we localize. So in this situation, as we've already mentioned, the multiplier decays like xc to the minus 1/2. And also what happens when we take, so you'll remember in the previous analysis, it's very important to also take the Fourier transform in the t variable. So here we're going to do exactly the same thing. We're going to take the xc tau Fourier transform, or the xt Fourier transform. And when we do this, okay, so now we're looking at some object in R4. And what we see is that we're supported in a neighborhood of a three-dimensional cone in R4, okay, with this particular localization I've described here. So this is very, very much analogous to the situation we had for the circular maximal function. We have the same decay rate from the multiplier, and we have the same kind of dimensionality. There we're localized near a two-dimensional cone in R3. Here we're localized near a three-dimensional cone in R4. And it basically turns out you can carry out kind of similar arguments to what used to study the circular maximal function to deal with this part of the operator. And this was exploited in the work of Pramanik and Seeger, which was kind of an early example of an application of decoupling inequalities, where they kind of very cleverly used all the two-dimensional theory, but lifted up in a higher dimension using lots of nice scalings and stuff to get their result for the range p bigger than 4. Okay, and we use off the shelf that these estimates of Pramanik and Seeger to deal with this part of the operator. So now there's the other case, the critical case, where we're really close to this degenerate cone sigma 2. And this turns out to be the crux of our analysis. This is the part of the operator that wasn't effectively dealt with before by Pramanik and Seeger. So now we're going to imagine localizing our operator A lambda f to xe close to sigma 2. So we're going to be really close to this binomial cone. And it turns out the definition of close is distance lambda 1/3. Okay, so this lambda 1/3 parameter is motivated by when you think about stationary phase. And this is the smaller scale at which it makes sense to localize. So in this case, we're in this critical regime where the multiplier has a degenerate critical point. So we only have this lambda minus 1/3 decay. So the multiplier is behaving a lot worse. When we try to exploit the decay, we're going to get a slower decay. Well, when we pull out the power of lambda, it's going to be a lambda minus 1. It's going to be a smaller power of lambda minus 1 coming out. So this is behaving a lot worse than the other situation. However, we do have a saving grace here. We are localized to this very thin region in the frequency space. So we have to exploit this additional localization, okay? The fact that this slow decay rate only happens in a narrow range of directions in the three-dimensional Euclidean space. And how this manifests itself is that when we take the xe tau Fourier transform, we are now localized to a neighborhood of a two-dimensional cone in R4. So previously we were localized to a neighborhood of a three-dimensional cone in R4, but now we're localized to a neighborhood of a two-dimensional cone in R4. And in fact, this cone has some geometric significance, but it's a little bit circuitous, like how you can interpret this geometrically. But it corresponds to a trinominal cone associated to some curve related to our original gamma, but lifted to R4 in some way. Okay. So now what we can do is we can develop the appropriate square function theory and kind of nicodem maximal function estimates, which are adapted now to this geometry of this two-dimensional cone in R4. And it turns out that you get kind of nice numerology, which allows you to deal with this part of the operator, despite the fact that you have this slow decay rate. Okay, and so in order to deal with this, we used all these modern tools in harmonic analysis, such as induction on scale methods, multilinear estimates. So it was kind of using this theory developed by Bourgain and variants that due to Lee and Vargas used to prove square function estimates. And in particular, a key ingredient was a multilinear restriction estimate, which the whole thing hinges on, which appears in the work of Bennett, Bears, Flock and Lee from a few years ago. Okay. So these are the two extreme cases. Is there any questions about this before I move on to the last bit? Okay, these are the two extreme cases, but actually what turned out to be at least the most difficult for us, I don't know whether it's maybe psychologically more difficult or whether it's actually more difficult, but the most difficult case for us was the intermediate case, where we're not miles away from this critical cone, but we're not on top of it, we're somewhere in the middle. So we now assume our operator is localized at some fixed distance from this sigma 2. So we'll do some kind of dyadic decomposition like this. So say we're at size 2 to the j away from this cone sigma 2 in some region of width 2 to the j. Okay. And so like I said, for us, this was the most difficult case to take into account. And really what we need to do here is we need to take the best features of both extreme cases and combine them together. So we'll get an improved decay rate for our multiplier coming from the fact that we're far away from this sigma 2 cone. Okay, so we'll beat the xe to the minus 1/3 decay rate, but we won't quite beat xe to the minus 1/2. And we also have some improved Fourier localization coming from the fact that, okay, although we're far away from sigma 2, we're still in some neighborhood of sigma 2, okay, because it's the nature of this dyadic decomposition. And we have to exploit that also. And basically it requires concatenation of the arguments that are used to study these two extreme cases. But these two different arguments they don't love each other very much. They don't want to fit together. And the reason for that is our analysis really hinges on using square functions And if you ever try these kind of reverse square function inequalities, and if you try to concatenate these reverse square function inequalities, you have a lot of trouble. They don't want to concatenate with one another. Okay, this is one of the reasons why like proving these sharp square function estimates is so difficult, because it's hard to iterate them. And but we managed to get through this by kind of concatenating these square functions in a kind of trivial way. In fact, we basically at one point in the argument, we basically use a kind of Cauchy-Schwarz square function inequality, kind of like a trivial square function inequality, which presumably introduces some losses into our argument. So our it's very unlikely that that the kind of estimates that we get are sharp, but they're still strong enough to prove this this helical maximal function theorem. And so one thing, I think this is probably the last thing I want to mention. Because I'm over time. So one thing that really, well, for me was very nice, that we exploited in our argument was certain weighted estimates for forward square functions. So this is a different kind of square function, plays a different role in a different part of an argument. But these square functions were proved by estimates were proved, or the technique for proving them was introduced by Carberry and Seeger in the early 90s, and it's like a very primordial version of this induction on scale technique. And this turned out to be extremely useful for us. It was a bit of a saving grace later in the project. Okay, so that's everything I have to say. Thanks very much. If you've got any questions, I'd be very happy to try and answer.